Hey, how's it going? Last time I talked a little bit about electric circuits, electric current, and I gave an example of this right here. So if you want to hear me talk a little bit about this, go back and look at the episode before this. But today, so this time I'm going to talk a little bit about AC and DC. I'm going to talk about the concept of voltage. And if there's time, I'll introduce power and energy. All right, let's call this EE 101, episode 2, AC/DC, voltage, and power. So, what are AC and DC? Well, these are abbreviations, or they're short acronyms for two phrases: direct current and AC alternating current. So what do these mean? Well, first, let's imagine we have a time function of current, I of t. This is a time function of current. Now, using this function, can we somehow define whether or not it's AC or DC? So let's look at a plot of this function, I of t, against time. And what's the definition of a DC current? Well, that's it. That's all it is right there. If you look at it visually, there's this current, and for lack of a better word, it's constant. A DC current is constant in time. It's a current, like I described in the previous episode, with a constant amplitude in time. The mathematically elegant way to write this would be its derivative equals 0, or it has no rate of change in time. It's a current with a constant amplitude. And that's really all there is to it. Understanding DC current really is that simple. It's probably exactly what you were thinking when I described current in the last episode, and that's really all it is. If I left it at that, there's a fairly large subset of the field of electrical engineering that we could just discuss in terms of DC current. Now, if you want to understand more complex systems, you really have to start talking about AC, and in my opinion, all interesting circuits are AC circuits. So we're going to have to introduce this concept. And I want to be careful here before I go into this. This isn't to say that the only types of current you can have in a circuit are DC and AC. These are two fundamental concepts you need to understand as we move forward in electrical engineering, but they're by no means all-encompassing. They'll get you very far, but it's not like these are just the end-all be-all. There's going to be situations where you can't describe what's happening with just DC or just AC or even a combination of both. But nonetheless, these are very important and will get us 90% of the way, 90% of the time. So let's talk a little bit more about them. So what do I mean when I say AC? Well, as you can probably imagine, if this is a direct current that has no variation in time, an alternating current might alternate in time. So first, let me draw an example of this function I of t. If it were an AC current, it might look something like this, and forgive my handwriting. And so part of what's really important here is that this function, as it alternates or oscillates in time, is that it crosses the x-axis, which means it moves about this zero current point. What do you think a negative current might mean? Well, if you remember from how I defined current in the last video, the plus or the minus sign is really just a vector. It describes the direction of the current flow. So as this function oscillates around this zero crossing in time, what that's really describing is a change of direction of the current in the circuit. And that's really important because it's a physical phenomenon. There is a current. There are particles with charge. They're flowing through our circuit, and they're actually changing direction with respect to this function. So then the natural question might be, to draw an elegant definition of AC current, is it as simple as the contrary to DC? Is it as simple as saying this? The time derivative of the current does not equal 0? Well, it's not that easy, and I'll explain why in a second. So the example of AC current I just gave is really only one specific kind of AC current. It's a sinusoid, and AC is just more general than that. All it means is that the current changes direction. It doesn't have to be sinusoidal or take any particular mathematical form, other than that it has zero crossings. So let me give another example of what an AC current might look like. If we draw I of t, okay, there's our zero crossing. It doesn't have to be a perfect sinusoid. You could have something like this. What about a sawtooth waveform? Or, let me give another example here. And you've probably seen waveforms like this before. But what if you have a square wave? Now there is some mathematical discussion you can have around whether or not these are actually just sinusoids. And we'll get to that much, much, much farther down the line. But the point is, these are AC currents, and you can't necessarily draw a conclusive definition around whether or not these conform to what I wrote on the last page. So can you just write a single expression in terms of their derivative that tells you whether or not these are AC currents? Well, if you look at certain moments in time, the derivative of this function is 0. And if you look at certain moments in time, this function doesn't even have a derivative. So, although it may not be mathematically astute, let's say, my best advice to you would be to simply check if the function has zero crossings. Now, there is a little bit more to it than that even. It's not just as simple as does this function have zero crossings. Remember I said there's a lot more to our current analysis than just DC and AC. So there's certain currents that just don't meet either description. So another fundamental component of what we might call an AC current, or at least in the context of how we care to analyze it, or any useful AC current in many aspects of electrical engineering, usually we're concerned with periodicity. So it's not just as simple as, are there zero crossings, or is there a single zero crossing? No, is it periodic in nature is usually what we care about when we talk about an AC current. So these waveforms, assuming they continue for any meaningful amount of time, you would say are periodic. This sawtooth is periodic. This square wave is periodic, and the sinusoid I drew on the last page is periodic. That's usually what we're talking about when we say AC. It's something with zero crossings, describing that the current actually changes direction, and it's something that's time periodic. Okay, now let me give one more example that hopefully gives a little bit more insight into what I'm talking about. I want you to answer this question for yourself about whether or not this current is AC or DC. Well, what do you think? It's definitely periodic. You could say there's a sinusoidal component to this current. But does it actually change direction? And if you think about it, no, it doesn't. And now this can get kind of hard to visualize, but if you imagine a circuit, what you're really seeing here is a net positive flow. So if you have a DC current, one thing to remember is that that current just flows in a single direction forever, or as long as it's DC, it just flows in a single direction. Now this current, although there is this ripple, does it ever actually change direction? And the answer is no. It may vary in amplitude in the direction that it flows, but it never actually changes direction. So this current as a whole, you can't say it's AC. But is it DC? Well, not exactly. So like I was saying, this is just one example of a current that it doesn't necessarily make sense to describe as AC or DC alone. And so this leads me to a technique, or rather a perspective, that you as an electrical engineer should have when you look at circuits, when you look at current, when you look at mathematics, and that's to see when and where you can apply principles of linearity and superposition. So if you look at this current, you can see it for what it is as a whole, and it may or may not be valuable to you to analyze it that way. But something that's usually incredibly valuable for an engineer to employ is, like I said, the principle of superposition. So you can look at this current and see it for what it is, or you can describe it as the combination of other currents. And it's not always convenient to do that, but in this case it really is. So how I would describe this really is I would say I of t is the summation of two currents. It's one current, A, a constant in time, plus another current, B of t. That varies in time. And so you could say, yeah, this current here, there's some constant DC offset. And about that DC offset, there's a small AC ripple. And so if I were to draw these currents A and B of t independently, let me scoot that up. This is what that might look like in time. So the current A is DC, and this captures really the large offset up in the positive direction. So this would be the current with amplitude A, DC. And then down here, about your zero crossing, if this is a purely AC sinusoid, which we decompose from this current I, B of t would look like this, with the same amplitude and periodicity you see here. Excuse my inability to redraw this. But so this is A, and this little wiggle would be B of t. And so you can describe this mathematically like this, assuming you had some DC flow and then added this AC ripple. If you add these two currents together, you'll get this right here. Okay, now let me give one more example of a general case current that may not be expressible as either just AC or DC or even a combination of both. What if you don't have a current that's periodic? Or what if it's periodic but not for infinite time? Can you really describe that as an AC signal? So let me draw an example waveform to capture what I'm talking about here. What if you have a current that starts off like this and then falls down and reaches zero at some point in time? Would you say this is DC, or would you say this is AC? Well, certainly not, assuming this is all time. This is the only current that you ever experience at whatever point in your circuit you're measuring it. Well, is this either? And the answer is no. And the way that an electrical engineer would describe this current is called a transient. Now, what does transient mean? Now, a simple definition is really just lasting for a short or finite time, or we can just say existing for some moment in time, something that occurs, it's a function of time, and really, as a function of time is the only way you can describe it. A really nice property of AC signals, assuming they're sinusoids or something periodic, is that we can usually talk about them in the frequency domain, and it's something that becomes very, very useful and also fundamental to a lot of analysis and electrical engineering. And I know this is just the beginning, but it's something to keep in mind. If I had drawn some signal like this, or any combination of, wow, that's really bad, or any combination of periodic signal like I drew on the last page, we can express these things as example. What if it's cosine x? Well, let's say I of x. And I know this is and I know this is sine here. Let me start one like that there. That one's cosine. But yeah, you get my point. This is a function that's periodic. And if you can't describe your signal or parts of your signal in this way, it becomes very difficult to talk about. And there's some signals in reality and electrical engineering that you'll only ever be able to describe fully in the time domain. Or at least you might have to approximate them in the frequency domain, but you're going to lose information. I know I'm totally getting off into the weeds here, but I just want to leave this as a remembrance so that you know what to expect going forward. And one last disclaimer, transient doesn't necessarily mean your signal isn't AC. This is just really the only way you can describe a signal that's neither AC nor DC. You can definitely talk about AC signals as transients or in the time domain. It's just that transient or time domain analysis is the most general case of analysis that we can use when we analyze waveforms, currents, voltages, signals, or anything in our circuits in electrical engineering. So just remember that.